This is a video for AQA Mechanics. This is circular motion section 2.4, horizontal motion on a sloping surface. Well, here we see an example of a bead which is rolling round the inside of a bowl. The fourth diagram there shows that the acceleration is towards the center of the circle, so it's in the horizontal plane that it's moving. But of course the forces themselves are acting vertically downwards, which is the weight, and then a normal reaction which is acting out of the surface at right angles to the surface itself. Now that's an idealized example where we've decided that friction is going to be negligible in that case. Of course, usually what we would have is that friction would cause the object to slow down, and therefore it would start to go down into the bottom of the bowl. But our diagram shows the forces that are acting, normal reaction and mg, the weight, and they give, as usual, a resultant towards the center of the circle to produce the centripetal acceleration. We find a similar situation to that in real life, which is with cars going around banked tracks, not necessarily as banked as this would be on a motor racing circuit. However, in general, roads are banked slightly towards the center of the circle that you're moving around. The reason for that is, of course, that we can then aid the centripetal acceleration, or the force required, and not need friction. If we're on a horizontal surface, then the force towards the center would have to be produced by a frictional force. So we'd have friction acting here to produce the horizontal force mv squared over r. And of course, as you move faster, the frictional force would need to increase. When we're on a banked track, however, then the weight is acting down mg, and then there's a normal reaction acting out of the plane, and that has a component towards the center of the circle. So this time it's this r which has got a component which is towards the center of the circle, and that can produce the centripetal acceleration. And that doesn't then require a frictional force. Of course, if you go too fast, then frictional forces will come into play. Let's look at that in practice then. This time a car is travelling around a bend, radius 300 meters, which is on a road which is banked at 15 degrees. If there's no tendency to slip up or down the slope, then we have just those two forces, no frictional force acting, so the normal reaction R and the weight mg, and those are producing the centripetal acceleration. So we can solve this then by resolving. First of all, let's resolve vertically. If we do that, we can see that the component in the vertical direction, this angle here, will be 15 degrees. So we can see that R cosine of 15 degrees must be equal to the weight mg. And so R cosine 15 degrees equals mg is the vertical resolution. If we resolve horizontally, then R sine 15 degrees will be equal to the value of mv squared over r, that's the centripetal force. And if we divide those two, then we can see that we have that tan 15 degrees on the left hand side is equal to v squared divided by RG. So that's the first equation, number 1 and number 2. And what we've done there to get the tangent is to do 2 divided by 1. So therefore tan 15 is V squared over RG. We know that R is equal to 300 in the question. We've got 300 meters for R, and therefore we can see that V squared is equal to 300 multiplied by G tan 15, and that gives us a value of V equal to 28.1 meters per second. So a standard way of solving this then, resolving vertically, resolving horizontally, and then there we didn't know R, or either of the R's, either the normal reaction, beg your pardon, or V, and therefore we could eliminate R from our equation here by dividing. And there we are, typed out. We might consider now what happens if you're going faster than our value of 28.1 meters per second. And of course, if we are, then if V is greater than 28.1 meters per second, then the centripetal force has got to increase. There's the acceleration will be greater, and therefore we will need a greater force. The only way that we're going to get an extra force is to introduce a frictional force, and so we would need then a frictional force which will act down the slope here, and that will then have a component towards the center of the circle. If on the other hand we've got a situation where it's going slower, so this time V is less than 28.1, then of course we've got to have a smaller centripetal force. That means that there's going to be a must then be a frictional force which is acting this time up the slope, and that will have a component acting away from the center of the circle, so that will reduce the centripetal force. So in both those cases then that we've just looked at, where a frictional force involved, obviously the frictional force can only increase to a certain amount. So if you're going too slow around here, then the frictional force can't increase anymore, and therefore you will slide down the bank. If you're going too fast, going back to the previous one, then you would slide up the slope. What happens in practice with bank tracks, of course you might have seen this with circular tracks for cycling, is that the banking is actually changing as it goes up. So instead of being a straight slope, the banking increases like this, and that means that as you rise higher up the bank, the force produced by the normal reaction is giving a greater resolve component towards the center. Hence the frictional force doesn't need to increase as you go faster, you just simply climb up the bank further. That's the end of this particular video. The next one we'll be looking at the motion in a vertical circle.